Hey everybody, we're going to take a look at section 9.6 on the counting principles. How many different ways can you do things, going back over some of those fundamental principles, and then a difference between permutations and combinations. So our end result for today is to try to figure out how many different ways are there to do something, like how many options are there to help us then when we move forward into things like probability, which is how likely something is to happen. So we need to be able to count first, which seems like it should be pretty easy, but sometimes counting can get a little tricky. So let's make sure that we're okay. So let's talk about the simple counting problems. So we have to deal with this idea of, we'll call it independent and dependent, or is there replacement or isn't there? Like, what do I have to choose from? So let's take a look at the scenario. If two balls are randomly drawn from a bag, because again, everybody's walking around with just bags of stuff, right, to pull things out. So say there's 6 balls and they're numbered 1 through 6. If it's possible to choose 2 threes, that means there must have been a replacement. We must have put the ball back. So we have this idea of we can take something out and we can put it back into the mix. So the only way we'd be able to draw 2 threes is if we draw the 3 out and then we put it back in so we can draw it again. If you're going to select the 2 balls from the bag at the same time, or take out one, don't put it back, and then take out the next one, then you're not going to be able to get 2 threes. That wouldn't happen if there's only 1 3 in the bag. So that would be without replacement. So kind of the difference between we will say independent versus dependent. If you can, every single time you have everything to choose from, we must have put it back in there, or they're all independent. What I do first doesn't really affect what happens next. If I do something that does affect what happens next, that's like that without replacement. Like I have fewer things to choose from. It's dependent on what happens before it. So we're going to be adding several examples. Feel free to pause the video so you can get what you need, but let's just take a peek at this scenario. So you're going to put 8 slips of paper numbering 1 through 8 in a box. We're going to replace the paper every time we draw a piece out. So then you're going to draw a second piece, but you're going to put it back so it's with replacement. So you have the total number you're still choosing from. And then you're going to add the 2 numbers that you get. How many different ways can you obtain a sum of 14? So your slips are numbered 1 through 8. So think about all the different ways you could get an 8. Well, we could have a 6 first on the first slip of paper and then an 8. We could get a 7, and remember we're putting it back, so we could get a 7 again. Or we could get an 8 the first time, and then we draw a 6. So with replacement, there'd actually be 3 different ways that we could get a sum of 14. What if instead I don't replace it? So same scenario to get a sum of 14. Well, I could get a 6 first and then an 8. Or I could have drawn an 8 first and then a 6. So would I have been able to do that 7 and 7? Well, no, because once I take out the 7, I don't have another 7 to draw, so then there's only 2 ways. So without replacement lowers the number of options that I have, right, to be able to figure out what those different options are. Okay, let's talk about a little bit more involved counting. So we look at different events and how they can happen, and then how would they happen together. So they're going to use some variables here, but basically what it says this. If an event occurs, so they're calling it E1, and it can happen in M ways, whatever M is, 15 different ways it can happen, 12 different ways, whatever. Then you have a second event occurs M2 ways, so however many ways it is, and E3 in M3 ways. The number of ways that all 3 events occur is the product of those 3 numbers. It's basically a shortcut for you having to multiply everything out, so being able to look at what that would be. So it's a product. If there were 15 events happening, you'd multiply all 15 ways together. So it's a shortcut for actually listing them all out. It works really well. So let's take a look at some of the examples you may have done earlier in your mathematical careers here with that. So we're going to have some breakfast. Love eating breakfast out. Always a great meal to eat out. So you have a choice of 4 different types of meats, so like sausage, bacon, whatever, 8 different styles of eggs, and 5 different types of breads. You're going to make a breakfast sandwich. How many different plates can you make? Well, let's talk about the things we have choice over. Different meats to choose from, different styles of eggs, and different styles of bread. All right, well, if you have 4 different options here, 8 different options there, and 5 different options there, the counting principle would say multiply those together. So how many different combination plates would be possible? Well, that would be 160 then, just multiply them together. Now that's a shortcut for actually making the list. So say I'll just make up something. So say you could have sausage and then scrambled eggs, and then you're going to have white bread. Or you can have sausage and scrambled eggs and rye bread, and you can have sausage and scrambled egg, right? And you can go through that entire list. If you listed all of these different possibilities, it comes out to be 160. So this counting principle is a shortcut for being able to do that arithmetic. So let's try a couple of those. So combination locks, so like the locks you have on your lockers in gym or whatever. So a combo lock will open when you select the right choice of 3 numbers. So there's a 3-number combo lock. How many different combinations are possible? Well, you can use the numbers on this particular lock, 1 through 30 inclusive. That means 1 is included and 30, so you can have any of those numbers. All right, well, the number of combinations possible then will be how many choices on each of those numbers, so each time you spin. Well, how many choices do you have for your first number? Well, you have 30 different options, right? The numbers 1 through 30. Now, the question is, can you repeat numbers? Could you have a combo that was 15, 15, 15? Most likely, yes. So if you can repeat numbers, so we're going to make that assumption here. That means there'd be 30 options on the next one and 30 on the next one. So the counting principle would say to get the total number of ways, so instead of doing all the combinations like 1, 1, 1, 1, 1, 2, right, making the list, we can just multiply those together to get that value, which would be 27,000. It's quite a bit if you think about it, just for three numbers only going 1 through 30. So we're looking at how many ways we can do things. Let's try another one. Products catalog numbers made up of 1 letter. So we have a letter first, followed by a 5-digit number. So for me, you're going to see me do this a lot. I really like to have visuals for these. It really helps me kind of lay things out. So this is going to be a number. Each of these are a digit. All right, so let's talk about our choices. So we make up the catalog number. The first thing's a letter. So how many letters in the English language? Well, 26. So we have 26 different options. A 5-digit number. So again, we need to have this conversation. Can the numbers repeat? For example, could you have a product number that's 11111? Probably. So we'll talk about if it can repeat. How many choices do you have for each digit? Well, you have the digits 0 through 9, which would be 10 total. So I would have 10 options for each one. The counting principle would say then I would multiply that together to find my options, which ends up to be 2,600,000. Now, how would it be different if they couldn't repeat? So you couldn't, once you had a 1 in your digit, you couldn't have anything after that. Well, you'd still have the 26 letters, but what would happen for the numbers? Let's take a peek. I'd still have 10 digits to start with, but after I use that digit, whatever it is, then I'm going to have 1 less option, 1 less option, 1 less option, 1 less option if I've already used it. So I would have fewer possibilities for those codes. So then it's only, if you multiply those out, only that many options. So this with repetition or no repetition really does matter in our calculations. So we'll always have to take a look at that and see what's happening. Excuse me, that's probably loud, sorry. All right, let's talk about the difference between permutations and combinations. Permutations are the number of different ways you can put things in order, so n elements can be ordered. So a permutation is that n factorial, which means, remember, you have 1 times 2 times 3 times 4 all the way up to n minus 1 times n. So for example, please add these because this really helps. Like if I were going to ask you how many ways can 8 students line up? So here are my 8 students. I have 8 choices for that first person, right? There's 8 people, but after I put the first person in line, then there's only 7 options, then 6, 5, and then 4, then 3, then 2, then 1. So 8 factorial. Now remember where to find those on your calculator. You have a couple options. You can go into math and over to probability, and it's number 4, or you can go into your function. Let's see, I think it's, yep, it is alpha F2, and probability is number 9. So you have, or permutations, I should say, factorial, help me, all of these are in there, so 7, 8, and 9. So you can go through and use any of those, so whichever is the easiest, just to make your calculation a little faster. So in this case, 8 factorial is 40,320. So if you're just putting things in a row, order matters, right? So let's make a big note here. Permutation, order matters. So the order that's selected is important. Okay, so let's take a look at what if you don't want to just put all 8 things in a row? What if you're taking just a small group from a set? So the number of ways that you can take a certain number. So they'll say n elements, take an r at a time. So n is the total number that you're choosing from. R is the number that you are choosing. Well, basically what that is then is it's taking the total ways you can arrange all of the things and dividing out the number of ways you can arrange the things that you aren't choosing, that n minus r. I'll show you what I mean by that when we do this example. It says, how many ways can a chairperson, a vice chairperson, and a secretary be chosen for a committee of 14 people? So notice why order matters. Order matters because it's different if you're the chairperson versus vice chair or secretary, right? You have different roles, so the order that you're selected matters. What that would be then is the n is the 14. You're choosing from 14 people. The r is 3. Now, if we were going to do this the old way, just counting principle, I would say, okay, how many choices do I have for the chairperson? 14. How many choices do I have for vice chair? Once I chose the president or the chairperson, only 13 left. And then how many would be left for secretary? It'd be 12. You could just do the counting principle, right? Multiply it out, and you would get 2184. But here's the cool thing about permutations. This would be 14 permutation 3. So we write the number we're choosing from, and the number we're choosing would be n factorial, so 14 factorial, over 14 minus 3 factorial. Watch what happens when you do that. We talked about factorials before. 14 minus 3 factorial is 11 factorial, right? Well, what's the difference between 14 factorial and 11? Well, 14 factorial just has three numbers first, and then 11 on down, right? And that's 11 on down. Watch what you have left. The exact same thing that we had when we did that counting principle. But again, the cool thing is about permutations, you don't have to write it out separately, right? We can just do that calculation on the calculator and think about really big numbers. It might be nice not to have to do that. So let's take a look at what that would be when we type it in. So it's really cool. On your calculator, you can just type in the two values and we can get that number. So when order matters, that's permutation. Okay, what about if there's repetitions in your permutations? What if things can't be told apart? So like you repeat numbers, you repeat letters. They call that distinguishable permutations, or a better way to say it would be indistinguishable, like you can't distinguish between things. So we're still looking at n factorial, but we have to divide out all the things that we couldn't tell apart, the repetitions. So let me give you a great example of something like that. Letters are a classic. When you look at the letters in the word committee, you got repeating M's, repeating T's, repeating E's. If I rewrite this, so if I say, okay, I'm going to take these and I'm going to rewrite them in a different order, and I wrote this, I can say I rearranged something. I switched the two T's, say. Would you be able to tell? Well, no, it writes the exact same word. So we're going to be counting some of the same words or the same arrangements of letters multiple times because I'm just switching the order of things that I can't tell apart, like the T's or the E's. So when we talk about repetitions, we're looking for things that are the same. So for this committee thing, we talk about how many letters are there total. Well, I think there's 9 if we count them. So if these were all just different letters, how many ways could you arrange the letters? It'd be 9 factorial if they were all different, but they're not. What do I have that repeats? Well, I have 2 M's. So what's the number of ways I can arrange 2 M's? Well, 2 factorial, right? MM, and then the other MM. I have 2 T's, same thing. So there's 2 factorial ways I can arrange those. There's 2 E's. So again, I got 2 of those. So I have to divide out the repetition. So anytime there's something that repeats, and then I can figure out that total. So it ends up to be, please try practicing typing all these in too. You can pause the video in between if you need to do that. We just divide out the things that we'd be overcounting. So in permutations, make sure we don't double count. Okay, so getting to that idea, how many distinguishable ways can the letters in, I love this, banana, always makes me think of the little minion guys, banana. How many different ways can that be written? Well, how many letters do you have total? So we count them up. So how many different letters are there in the word banana? 6, right? So that'd be 6 factorial. And then do we have any repetitions? Well, it looks like we have 3 A's. So how many ways can we arrange 3 A's? 3 factorial, right? Because we have 3 different letters arranging them. And then we have 2 N's, so 2 factorial. So there would be, looks like 60. So we can do the arithmetic and actually just to kind of prove, there they are. So all the different unique ways of arranging the letters in banana. And only one of them spells banana. So there you go. Got lots of fun ways to be able to do that. So 60 different options. All right. Let's go into our last little chunk here. So let's talk about a different kind of arrangement. So, how many ways could 3 letters be chosen from A, B, C, D, E if order doesn't matter? Show our reasoning. Well, what I would do is I would just start listing them. So, see if we can make a list. So, pause the video if you could and just write out all the different 3-letter patterns you could choose from this number if the order doesn't matter. In other words, if I write down A, B, C in that order, I don't also have to write down like B, C, A as a separate arrangement of it because I already have those 3 letters accounted for. So the double counting isn't necessary. So all the separate ones. So I could do ABC, I could do ABD, I could do ABE, all the ones starting with AB, and then I could do ACD, and I could do ACE. Now how about A and then a D? Those are all the ones that start with A. I could do BCD, so all the ones that start with B, BCE, BDE, and then CDE. I think that's everything, starting with A's, the B's, and the C's. Now noticing I don't have any of the repetitions where I just rearrange these in a different order. So if order doesn't matter, how many ways was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 ways. I chose from 5 items and I selected 3. But it isn't permutations now. This would be combinations. So that's kind of our last little piece. When order doesn't matter, the number of combinations, it's always less because we don't have to do all those different arrangements. So we still have our n factorial over n minus r factorial, but then we have to divide out also all the different ways that we could just rearrange the things that we're selecting. We don't need to count ABC and CBA as 2 separate things. They're the same letters. So for a combination, the order in which the elements are listed is not important. It doesn't matter. So for the example that we just did, this would have been 5 choose 3. So that would have been 5 factorial over 5 minus 3 factorial, 3 factorial. So that's 5 factorial over 2 factorial, 3 factorial. Go ahead and type that into your calculator, this 5 choose 3. I just want you to see what happens that we do in fact get our 10. So I'm going to go to my alpha. It's a little bit faster, number 8. Combination. So I'm doing 5 and choosing 3, and there's our 10 ways. So when the order doesn't matter, we always have fewer options to choose from. So let's go back. Remember the one we did, the chairperson, vice chair, secretary? Choosing from 14, choosing 3. Order doesn't matter though. So say you're just going to choose a group of 3 people to be on this team. It doesn't matter which one's getting selected first. They're just all going to be part of the team. Well, that would be 14 combinations 3. So let's see how that's different. So that would be 14 factorial over 14 minus 3 factorial, 3 factorial. So the difference is that extra number of ways we can arrange the things that we're selecting. So 14 factorial over 3 factorial times 11. Now again, I wouldn't probably do that. I would go back to my math menu here. So we're doing 14 choose 3. And if you compare those two numbers, 364 compared to what we had before, which was like 2184, it's a much smaller number. So when the order doesn't matter, gosh, that's going to be a lot fewer choices to choose from. All right, let's take a look at our last couple examples. So we'll do a couple combinations. So we're going to play some cards. So I have all the cards here. We have hearts, diamonds, and then we have spades, and we have clubs. When I was little, I always said shovels and clovers, so it always messes me up when I look at those, but spades and clubs. All right, so you're going to draw 3 cards out of a hand of 52. How many different 3-card poker hands are there? Well, you're choosing from a group of 52 cards, and you're going to choose 3 of them. How you draw them, do you still have the same cards in your hand? Well, sure you do. It doesn't have to be in any particular order, so that would be a combination. So 52, choose 3. So when we do our 52, choose 3. Again, you can go back to your math menu here. So we're choosing from 52 cards, and we're choosing 3. So 22,100. Now, if this were permutations, gosh, that would be huge, right? We'd have lots of choices. All right, take a look at our last one. You're going to form a 12-member swim team from a group of 10 girls and 15 boys. And each team has to have 6 of each. So we have more people that can be on the team than than what we're going to end up choosing. So we're going to have to choose. We have to select people. How many different 12-member teams are possible? So we're going to look at the number of ways we can select the boys and the number of ways we can select the girls. Then the counting principle would say, okay, to get the total number of ways to do both, we're going to have to multiply those two numbers together. All right, so how many boys do we have to choose from? Well, it said there were 15 of them. So 15, and we're going to be choosing 6. Now, does order matter? Well, if you're picked first or 6th, aren't you still on the team? Now, if it said, hey, the first person selected is going to be captain, that would be different. So that's combination. Now, for girls, we only have 10 to choose from, and we're still choosing 6, and we're going to multiply those two options together. All right, so 15 choose 6. Go ahead and calculate that, and your 10 choose 6, calculate that. So 10 choose 6, 210 ways. And then we've got 5,005 ways. So together, it's over 1,000,000 ways. So 1,051,050. Tons of different ways. If it was permutations, it would be even more. So what we're looking at, you guys, is difference between permutations, combinations, how many ways can we do things, and then just being able to count. So we're going to be doing a lot more with this, but the big question always is, hey, does order matter? All right, so we're going to be doing our assignment. We'll be taking a look at that, working on that, and we'll keep rolling then the next section with probability.